uniqueness of finite fields. Okay. Before moving on to uniqueness of finite fields, let me give a sort of a definition that if I have a field f and I have two extensions, let's say one extension is E, let's say another extension is E prime. Okay. Then we say that the extension E mod f is isomorphic to the extension E prime over f. That is, these two field extensions are isomorphic if there exists an isomorphism uh, from E to E prime, say phi, such that phi restricted to f is the identity map. Okay, clear? So phi fixes every element of the field, and phi is an isomorphism between E and E prime. In that case, we say that the fields are isomorphic, and rather the field extension is an isomorphic extension. Okay. Now, when we are talking about finite fields, if you go for a quick recall, then the whole concept of finite fields is typically based upon the fact that the prime field ZP is existing within it, if you recall, right? So, in order to have the uniqueness of a finite field, what we need to claim is that if I have a field E and a field E prime, both are uh, of the same order, say p to the power n, then what I claim is the following. Okay, so given E and E prime of order p to the power n, then there exists an isomorphism. Okay, there exists an isomorphism from E to E prime, let's say phi, which fixes its prime field Fp. Okay, okay. Let me change the nib of my pen. Yeah. So fine. So this is my claim, right? This is my claim. Let's prove it. Okay. Do I have page beneath? No. Right. Let's prove it. Proof. Okay. Now recall in the previous lecture we had proved that the multiplicative group of any finite field of order p to the power n, it actually it admits the form uh, 1 alpha alpha squared, right? One second. 1 alpha alpha squared till alpha to the power p to the power n minus 1, right? For some alpha in E cross, right? We had proved, in fact, we had proved basically a stronger statement that if F is a field, then any finite subgroup of its multiplicative group is cyclic, right? So if it's a finite field, then its multiplicative group is automatically finite, a subgroup of itself, so it will be cyclic as well, right? Fine. So we will make use of this. Now, if E cross takes up this form, then it immediately implies that E is actually the field Fp, which is prime field that is sitting inside it, the smallest field sitting in smallest subfield of it, the intersection of all the subfields of E, or rather the smallest subfield of E in some sense, it adjoined to alpha, right? Yeah. Because if you recall, how were we trying to construct this field E? We were trying to construct E as the splitting field, as the splitting field of t to the power p to the power n minus t, right? And we were taking this polynomial from Fp, recall Fpt, right? So the root it carries, right? Using those, we were trying to construct E. We had proved that this has all distinct roots. Recall, this has all distinct roots, right? And then we had proved that the collection of all the roots of this polynomial, it actually forms a field, right? So there would be exactly p to the power n roots, and that field will give you the field of order p to the power n. So in some sense, I think I had mentioned this term of splitting field. So the splitting field of this polynomial over Fp will give you the field of order p to the power n. And what the basic thing we do is that the non-trivial root which it admits, which is inside the splitting field, if I just adjoin that element to Fp, right, it will give me the whole field E, right? Why? Because just we had shown in the previous lecture that the multiplicative group is actually cyclic, right? So every element, or rather you can think of it in this way, that um, what I want to say is basically that you can generate every other root with a power of alpha, right? Getting my point? So every element should be some linear combination of alphas along with the other elements of Fp. That is what exactly I mean, right? So this is just Fp adjoint. Okay. If you're getting confused with this proof, just take it for granted for the time being. Later we will be coming up with a detailed course on fields, then this will be made clear. This will be covered again. Okay, no problem. Another, yeah. So we have this. Now let phi be a map from FPT to E by, okay, I'm trying to explain it a bit. Let's see. FPT to E by say mapping T to alpha. I can do this, right? Then observe that this implies that there exists a map phi bar from FPT mod PT to E, where PT basically generates the kernel of this map phi. Okay, so PT is an irreducible polynomial, right, which generates the kernel of phi. Such structures we have dealt with in the previous lecture itself, if you recall, right? Also, phi bar t is equals to alpha means that alpha is a root of PT in E. Alpha is a root of PT in E, right? But what does this imply? This implies that PT and t to the power p to the power n minus t, this is not equal to 1 in PT, right? Because both are giving the same roots. Okay? Alpha is also a root of PT, alpha is also a root of t to the power p to the power n minus 1. So x minus alpha at least needs to be a common factor, so it cannot be equal to 1, right? Got you getting my point? So, and we had also proved it that, if a GCD holds in some higher ring, it should hold in the lower ring as well, right? So therefore, or at least GCD is holding in a lower ring, it should hold in an upper ring as well over polynomial rings over field. Or at least what I want to claim is that since it's non-trivial in a higher ring, it should be non-trivial in a lower ring, right? And by ring I mean polynomials over fields. Okay, so that means that PT, the GCD of PT and t to the power n minus t, this should be non-trivial in FPT as well, right? What does this mean? So this means that t to the power p to the power n minus t is a product of linear factors, right, in E prime, because FPT, or what I want to say is the following, because FPT, or rather FP, is also extended to E prime by our hypothesis. Getting my point? So since it's non-trivial in FPT, it should again be non-trivial in E prime. Getting my point? So it must be a product of linear factors in E prime, right? Therefore, what does this imply? Therefore, PT has a root in E prime. Has a root in E prime. Are you getting my point? What I'm trying to say? Look closely. See, E prime is also a field of order p to the power n. So in some sense, it's also a splitting field of t to the power p to the power n minus t. Right. Therefore, this polynomial should split in E prime. And since the GCD of pt and t to the power p to the power n minus t is not equal to 1 in fp, it should be not equal to 1 in ept as well. Sorry, E prime t as well. Because E prime is again an extension of ft. It's again a finite field, right? Right. So now since t to the power p to the power n minus t splits over E prime, right? Therefore, and the GCD of pt and t to the power p to the power n minus t is not equal to 1, they must share at least one common factor. That common factor has to be alpha. Or rather, we haven't claimed that yet, but let it be for the time being. But at least what we can say is that pt has a root in E prime, right? Pt has a root in E prime. So let the root in root of pt in E prime be alpha prime. Okay, let's say. Now we can define phi prime from fpt to E prime by just mapping t to alpha prime, the same mapping. Okay, what we'll be having from here, then immediately what we can observe is that therefore the kernel of E prime should contain the ideal generated by pt. Now see, what is the reason behind that? See, this pt p is an irreducible polynomial, right? So therefore the ideal generated by p should be a maximal ideal. This should be a maximal ideal. I don't remember whether we had discussed this rigorously in the previous lecture when we had introduced the notions of prime ideals or maximal ideals, but nevertheless we will do this in this lecture at least. So what you can think of now is that the ideal generated by an irreducible polynomial is a maximal ideal, right? And since the kernel of phi prime is contained in pt and phi prime is obviously a non-zero ideal, so that means, or rather I don't mean a non-zero ideal, I mean non-trivial ideal, because phi prime is a non-zero map. That means the kernel of phi prime, it cannot be equal to the whole ring, right? Therefore, it has to be pt by maximality, What does this imply? This implies that E prime is isomorphic to FPT by PT. And from here the proof is trivial, right? Because what we have proved, so we have proved that E prime, uh, you know, I have a map phi prime bar which admits the isomorphism PT, and there I also had a map phi bar to E, and you can immediately observe that both these maps, phi prime bar and phi, these are both identity on F, right? Because I am mapping the element T to alpha over FP, all these are constants. There's nothing to prove. It will map constants to constants, right? It's identity over FP, right? So what does this imply? That E prime is isomorphic to E by the composition of the maps phi bar and phi prime bar. Clear? Therefore, what we conclude from here is that finite fields uh, of order p to the power n are unique up to isomorphism. Okay, fine. Now let us move on to the domains which we want to talk about in this lecture. Okay, yeah. So uh, the special domains. Special domains. Now first let us get back to Z. Okay, one of the important properties of Z are the following. One is that there exists a division algorithm in Z. Okay, this is first thing. The second important property is that every ideal in Z is a principal ideal, we call, right? And thirdly, we also have the fact that division in Z is unique, right? Unique in terms of the quotients and the remainders, if you recall. Uh, yeah, so I wouldn't say in terms of, yeah, it's basically unique up to units, a multiplication by units. We'll get into that. What I want to say is the following. See, uh, if you have, say, A is equals to BQ plus R, so you say BQ1 plus R1, and you also have it as BQ2 plus R2, right? So from here, what you can see. So this implies that B times Q1 minus Q2 plus R1 minus R2 is equal to 0. What can we immediately conclude from here? So it's basically you are dividing 0, right? See, from here you can write B times Q1 minus Q2 must be equals to R2 minus R1. And what is the additional condition you have? That the degree of each Ri is less than the degree of B, right? Or in this case you do not have the degree, in this case you have the value typically, that R must be less than B in this case, right? I just went back to the notion of polynomials. But if R is less than B, and if you observe it clearly, then what can we immediately conclude from here? That this needs to be 1, I mean 0. So rather R2 must be equals to R1, and that would immediately conclude that Q1 must be equals to T. Getting my point? Okay, fine. Right. Yeah. Okay. So the division, as I said, is unique in case of integers. Okay. Now, now there is also a very important notion in integers, which is the unique factorization. Factorization of numbers. Okay. And our usual factorization of numbers are basically what we call the prime factorization. So what I can do is that if I choose any number from integers, then I can factorize it into a product of primes. Right? I can factorize it into a product of primes. And the maximum I can do is a additional multiple of minus 1, right? So suppose I can write a number as say p1, p2 till pn, and so I can max to max, I can write it as say minus 1 times minus p1 times p2, p3 till pn, right? Or minus p2 an additional, or minus p3 an additional, but I can't change it anymore, right? This is the, and since we restrict ourselves to, in usual calculations, we restrict ourselves to positive integers. In case of that, the only factorization possible is this. And if I just restrict ourselves to all the possible integers, then our usual factorization will only allow us to an additional factor of minus 1. And one thing which you can observe is that minus 1 is a unit in C, right? Fine. Yeah. So keeping in mind the notion of division, we can talk about a very important sort of a domain called the Euclidean domain. Called the Euclidean domain. Okay. So what is a Euclidean domain? So Euclidean domain in very simple sense is a sort of an integral domain where a division algorithm exists. Okay, so any function n from a ring R, okay, which is an integral domain. All the rings which we got discussed in this lectures would be integral domains. Okay, so R is an integral domain. So from R to positive integers including 0 is called a norm. Is called a norm if n0 is equals to 0. Okay, it's called a positive norm if n of a is greater than 0 for all non-zero elements. Clear? Okay. Now we say R is an ED, that is an Euclidean domain, if there exists a norm on R, okay, such that for all AB in R, with say B not equal to 0, there exists elements Q and R in capital R, such that I can write A as BQ plus R with either R being 0 or the norm of R is less than the norm of B. Yeah. Okay. So this Q is what we call the quotient. Okay, and this R is what we call the remainder. Okay, easily observable, and we can immediately give two important examples which we have already discussed in previous lectures. Recall, one is integers is an Euclidean domain, right? There's a well-defined Euclid's division algorithm existing, and the polynomials over F. We had also proved that there is a division existing, right? The usual division of polynomials, if you recall. So these two are evidently Euclidean domains, right? Okay, yeah, fine. Now, one thing to immediately observe is that once you define such a division over any integral domain, so if you define A is equals to say BQ0 plus R0, then I can redivide B by R0 to write B as R0 Q1 plus R1. Then I can divide R0 by R1 as say R1 Q2 plus R2. I can continue doing this. Okay, I can continue doing this till I get Rn minus 2 equals to Rn minus 1 Qn plus Rn, right? And then Rn minus 1 is equals to Qn plus 1 Rn, right? Okay, and observe that this process must terminate finitely. Okay, you cannot keep on doing this continuously. Okay. This process must end finitely, right? Why is it so? Because see the norm of R, the norm of Rn plus 1. Sorry, we have chosen norm of Rn, right? The norm of Rn should be less than uh, the norm of Rn minus 2. Sorry, Rn minus 1, which should be less than the norm of Rn minus 2. Okay, let me just go back and say it in this case. Okay, see the norm of Rn must be less than the norm of Rn minus 1, right? Then if you go back to the previous step, then the norm of Rn minus 1, because in the previous step what we will be having is that we would be dividing Rn minus 3, right, by Rn minus 2, and we would be getting the remainder Rn minus 1. So Rn minus 1 would be less than uh, norm Rn minus 2. Continuing in this way, we will get this to be less than norm of R1, right? Wait. Right. Yeah. So norm of R1, which should be less than norm of A. Yeah, we were divided norm of B. Norm of B. Norm of R0. I missed the remainder. So yeah, R1 to R0 to a norm of B. So it's a so we start from here, right? So it's a decreasing sequence of norms, and each norm of Ri is a non-negative integer, and it's a strictly monotonically decreasing sequence. If you observe, it's a non-negative integer, right? And it's bounded below by 0. It's strictly monotonically decreasing. It must stop finitely, right? We can observe it immediately, right? So when it stops at this step, this divisor what we have, right, Rn, this will immediately give me what we had discussed to be the GCD of A and B, right? And the proof works exactly same as we did for the proof of GCD of polynomials, if you recall, right? We had given the same sort of a division algorithm, and then we did the same process to end to come to a point where there is no more remainder. The division becomes a trivial division, and in this case, what we had done was we had chosen the divisor, and it came out to see that it was itself the GCD, right? Because we can immediately see that if Rn divides Rn minus 1, then Rn will immediately divide Rn minus 2 from the previous step. Then Rn will divide Rn minus 3 from the previous step, and continuing, Rn will divide A and Rn will divide B, right? And if C is some other divisor of A and B, then if you go through the same steps again, C will divide Rn, right? It's very simple to observe that. Right? So in that case, what we can conclude is that in an Euclidean domain also GCDs always exist. Okay, so in an Euclidean domain, GCD exists, and this is what you called in your school days as the long division method. In terms of the long division method, right? Okay, so it's a it's a bit complicated to calculate GCDs in this case, but nevertheless you have to do it in some sense. These are the sort of things which you are pretty acquainted with your school days, right? Nothing complicated here. Getting my point? Okay. Yeah. Now observe the following. Fine. Getting hold of this. Now just see, we had said that Z is a Euclidean domain. I should have mentioned what norm is associated to it, but that is very easy to observe that norm of any integer you can choose it to be the modulus of that integer, absolute value of that integer. This will give you the well-defined norm. In case of fx, recall we had defined, but if you had watched the Euclidean division carefully, then the norm should be norm of any polynomial should be just the degree of it, right? Fine. Another important example we can talk about. See, suppose you are this. Suppose if you are in this integral domain R, and you move on to its fraction field. Okay. Then we know that every element in the fraction field is written in the form AB inverse, such that A and B come from R, and B is non-zero. So in that case, I can write A as BQ, right? Where Q comes from FR. This implies that every element of FR or every pair of elements of FR is divisible uh, till one of them is non-zero. Non-zero. In other sense, this forms an Euclidean domain with the norm being zero. Every element of the norm being zero. Yeah. Right. And basically, you don't just need to get into a specific field of fractions, but what you can do, you can talk about any field, and over any field, choosing the norm to be zero will do the job. Why is it so? Right? See, every element in a field can be written in this form trivially. Here, I just chose the example of a fraction field because by the construction of the fraction field, or rather keeping in mind the construction of the rationals from the integers, we know this, right? But a similar thing will obviously happen in case of any element, right? Why? Let me just explain in a brief. See, if you are in a field, if A is an element from a field except the zero element, then I know that I can write A inverse as 1. So I can write this as A times, so Q times, or rather, let's say A times A inverse times Q be equal to Q. So I can choose this to be B, right? Or I can choose this to be B inverse, so that B is equals to QA inverse. Q is non-zero. Sorry, Q inverse A. Right? In some sense, I'm talking about this. So every element you can write in this form. That is what I'm trying to mention. Nothing else. Got my point? Now, as we have talked about Euclidean domains, there is a very important observation which one can make in case of Euclidean domain. So, theorem, that is, every ideal in an Euclidean domain is a principal ideal. Okay, is a principal ideal. Okay. Let's prove. And the proof is exactly similar as we had proved that the ring of integers is a principal ideal domain, and the ring of polynomials over the fields are also principal ideal domains. What we are essentially proving here is that all Euclidean domains are principal ideal domains. And the proof is like this, that let I be an ideal in R is an Euclidean domain, and choose some element D in I such that the norm of D is the minimum, right? The minimum can be attained, right? Because it's a because norm always attains non-negative integers. So by Bain ordering principle, this will immediately hold is the minimum. Okay. Minimum across I. Right. Now, what we want to do is that now let A be an arbitrary element from I and divide A by D. Then this implies there exists Q and R in R such that I can write A as QD plus R. But this implies A minus QD is equals to R. Now, since A is in I, D is in I, so QD is in I because Q is an element of R and I is an ideal. So this implies A minus QD is in I, but this implies R is in I. But this should imply R is equals to 0. Why? Just recall that from the division algorithm we know that the norm of R is either less than the norm of D or it's exactly equal to 0. But this condition cannot hold, right? Because we have already chosen the norm of D in such a way that its norm is the minimum. So since R is in the ideal, its norm cannot be less than the norm of D. So only possibility for R is to be is for it to be equal to 0. Getting my point? So once R is equal to 0, what do we conclude? That A is an R multiple of D, right? So this means that A must be contained in the ideal generated by D, or I must be contained in the ideal generated by D. But since D is chosen from the ideal itself, I already contains the ideal generated by D, right? Therefore, this implies that I exactly must be equal to the ideal generated by D. Okay, proof is quite obvious. So what do we conclude from here? Conclusion is that all Euclidean domains are principal ideal domains. Okay, and the converse is not true. The converse is not true. Um, there is an example, but explaining that example is sort of a bit difficult because it requires talking about what we call universal side divisors and data kind Hasse norms. So let it be for the moment. Let me not talk about that. But there's an example, and that example is okay Z and to it being attached this element. Okay, this is the PID since it has a well-defined data kind Hasse norm. Okay, we won't talk about it, so I'm just writing it as a insight, but it's not an Euclidean domain. Okay, as we'll see that it doesn't, or rather we won't see this lecture, it's out of context for this course. It's it's some sort of a difficult calculation, difficult thing to explain in a general course on ring theory. But in some other lecture I'll try to come up. In some short lecture I'll try and explain why is it not an Euclidean domain but a PID. Okay. But let it be for now. Okay. Yeah, fine. So what I conclude from here is that the converse is not true. That is, every PID need not be an Euclidean domain. Fine. Okay. Fine. Let's continue. Now, one more thing which we can observe is that recall Zx is not a PID. Is not a PID, right? Because we had proved that the ideal generated by 2 and x is not a principal ideal. But what does this imply? This implies that Zx cannot be an Euclidean domain as well. It's not an Euclidean domain as well. Right? Fine. So what we conclude from the first part of this lecture is the following. What is an Euclidean domain? The division algorithm in an Euclidean domain, and that every Euclidean domain is a PID with a converse not being true. In fact, we have also proved that the GCDs always exist over Euclidean domains, right? And since we have already proven, so we had already talked about the definition of GCD in the previous lecture. I'm not going to introduce that anymore. But observe that the definition of GCD holds exactly in the same sense, right? Definition of GCD is in the same sense. As recall that in that case we had proved that so the basic definition of GCD is that if D divides the pair of elements and it is the greatest of all the common divisors, right? And we had there we had defined it to be the generator of the principal ideal of A and B in a PID. But now we have just proved that every Euclidean domain is a PID, right? And we have also proved that by using the division algorithm that there exists a GCD for every pair of elements. Therefore, we can also talk about the GCD in the same sense. That is, given two elements, check the ideal generated by those elements, and then find out its generator. Got getting my point? Okay, fine. Now, so I'll end the first part of this lecture. I will keep continuing doing it, but this is the first part of this lecture. Okay, you can see this lecture part by part, but I will pay for it to you to see it in one go. Okay, and the theorem is as follows. Okay, that let R be an integral domain, then uh, then for every pair of elements in R, their GCD is unique up to associates. Okay, what do we mean by associates? Associates means, so this is the definition of associates. So if we say A is an associate of B, and this is the symbol we use, if and only if there exists some unit U such that A is equals to UB. and you can verify that actually being associated is an equivalence relation. Right? You can check this. Since we are over commutative rings, it is not difficult to check it at any case. Fine. Yeah. So the proof is very simple. What we prove is first that the ideal generated by D and D prime, where D and D prime are arbitrary elements. Okay. This immediately implies that D must be U times D prime. Okay. Fine. Okay. You getting my point? Okay. Let's prove it. Proof. So we what? Yeah. So as I said, we will prove this. And the proof is quite simple. Why? Because let's say what do we do? Let me think of something. See, so I have D being equal to D prime. That means the element D is in D prime. That means I can write D as some R times D prime. Right. Okay. Pardon me. D is equal to some R times D prime. Okay. Fine. Also, what we can say is that D prime is in D. So this implies D prime can be some S times D. This implies I can write D as R times S times D, which implies D times Rs minus 1 is equals to 0, and which implies Rs must be equals to 1, which implies R is the unit. Since obviously D is non-zero. Right? I haven't assumed it, but still D needs to be non-zero. Right? Because if D is 0 and you take an ideal generated by some element D prime which equals the 0 ideal, so that element should obviously be 0. What's the point then? Right? Now what does this prove? This proves the following, that if I choose the GCD of two elements, then then we will have this, right? If both are GCDs of A and B. But that should imply that D prime is U times D. What does this imply? That D prime and D are associates. Clear? And this is also what we call unique up to associates. Okay, two elements, or rather two properties are unique up to associates if they hold for elements which are unit multiples of each other. Getting my point? Another way of describing the notion of associates is the following. See, recall, I think we had introduced it in some lecture that in some integral domain R, we say A divides B if there exists some element R in capital R such that B is equals to A times R. So A and B are associates if and only if, let's say, because it's a definition, A divides B and B divides. Okay, fine. And also, this division is said to be proper if R is not a unit. Okay. In some books, this is a extra definition given, but let's not be talking about that in specific. Yeah, fine. There is also a general notion of irreducibility which we need to introduce, but let it be there for now. Okay. Yeah. So we are meeting in the next part soon. Okay. Okay. Yeah. So moving on to principal ideal domains. Now we have already discussed about principal ideal domains previously. Okay. So principal ideal domains. Okay. So the only thing which we would like to do here is to give an essential, an important property of principal ideal domains. That's it. Okay. Because we have already discussed what principal ideal domains are. Every ideal is a principal ideal. Then we had proved, if you recall, that if f is a field, then fx is a principal ideal. Right. So what we want to do in this part is to talk about only some essential properties of principal ideals. Okay. I think in some previous lecture we had also proved that over principal ideals, every non-zero prime ideal is a maximal ideal. Right. So let's reprove that. Over a PID, every non-zero prime ideal is a maximal ideal. Right? Because we know that in an arbitrary ring, maximal ideals are always prime. Right? Because if M is a maximal ideal, then R mod M is a field, hence an integral domain, which implies that M is prime. Right? So this is sort of a converse restricted to PIDs. Right? I don't remember whether we had proved it or not, but let's see. Okay, so what we do is that we start with a non-zero prime ideal. So let 0 not equal to P be a prime ideal, right? And let I be an ideal which contains P and is contained in the ring R. Okay. Now since R is a PID, right? There exists some element M in R such that I is generated by that element. Okay. Now, so what we have is that P is an ideal in the ideal generated by M and it is an ideal in R. Okay. Now observe that now Since P is in the ideal generated by M, that implies I can write as P is equals to R times M for some R in R. Okay, fine. Since P should be contained in the ideal generated by itself, that implies Rm should be contained in the ideal generated by P. But this is the prime ideal. So that means either R is in P or M is in P. Right? Now observe that now if M is in P, then what can we conclude from here? Then that implies that the ideal generated by M is in P, and hence the ideal generated by M is exactly equal to the ideal generated by P. Else, if R is in P, in the ideal generated by P, then I can write R as some P times S. In that case, my P becomes, which was Rm, it becomes P times S times M. In that case, what we can conclude is that P times uh, 1 minus Sm is equal to 0. Since P generates a non-zero prime ideal or other non-zero ideal, so P cannot be a zero element. That implies 1 minus Sm is equals to 0, or which implies M is a unit. But M being a unit means the ideal generated by M is the holding R. Right? Thus, what we conclude is that P is a prime ideal, because if there exists an ideal which contains P, then that ideal must either be equal to the ideal generated by P or it must equal the whole ring. Right? Therefore, P is a maximal ideal. Now, this is a very important conclusion. Let's see. Conclusion. Okay. Observe that suppose R is a let's say a commutative ring with unity. Oh, we were always assuming it to be commutative ring with unity, so let R be a unity ring in our context, such that the polynomial ring over R is a PID. Okay. Therefore, fields will go well here. Right? If I choose R to be a field, then it's the polynomial ring over F is, we know that it's a PID. Fine, good to go. Then R is a field. R is necessarily a field. So if R is a ring, or rather a commutative ring with unity more explicitly, such that the polynomial ring over R is a principal ideal domain, then R must be a field. In some previous lecture, we had proved that if R is a field, then the polynomial ring over it is a PID. Here we prove the converse of it. And why is it true? The proof is very simple. Proof is that observe that if Rx is a PID, then the ideal generated by X is a maximal ideal. Why is it so? Because recall that the ideal generated by X is a prime ideal, non-zero prime ideal. Right? I think we had also introduced the notion of irreducibility in some previous lecture. Right? So X is irreducible, the ideal generated by X will be a prime ideal. Right? Because we were working in a PID. But you do not need to get into that. You can directly prove it is a prime ideal from here, because immediately observe that if Fx times Gx is is inside the ideal generated by X, then that means that F of 0 times G of 0 must be 0. Right? Because F of 0 times G of 0 must be X times some polynomial Hx. But we are obviously working in an integral domain, right? I had said in the first part of the lecture itself that we are working inside integral domains. So either F0 must be 0 or G0 must be 0. And that means that either X divides F or X divides G. That means either F is in the ideal generated by X or G is in the ideal generated by X. So it's a prime ideal. Right? It's a prime ideal. Okay. But what we have seen in a PID, that every non-zero prime ideal is a maximal ideal. Therefore, X is a maximal ideal. But then recall, we had also proved that Rx, mod the ideal generated by X, is isomorphic to R via the evaluation map at 0. Right? So if this is a field, this is a field, right? Because X is a maximal ideal, this will be a field. So R will be a field. Clear? Okay. Fine. Now let's move on to the next important part which we want to discuss is the notion of unique factorization domains. Okay. Let's see. So what are basically unique factorization domains? Before moving on to what we call unique factorization domains, let us just deal with a few definitions which we require. And this is sort of a recap. I think we had discussed this in the previous lectures itself, but nevertheless still do it. Okay. Let R be an integral domain. Suppose R in R is a non-zero unit. Sorry. Suppose R in R is a non-unit non-zero element. It's a non-unit non-zero element. Then R is said to be irreducible. R is said to be irreducible in R if whenever R is equals to A times B, with A and B coming from R, Either A is a unit or B is a unit. Either A is a unit or B is a unit. Yeah. Otherwise, we say that R is reducible. Otherwise, uh, R is reducible. Right? And we have already discussed about what we say about division, simple division. That is, we say A and B. A divides B if A is non-zero, and there exists an element R such that B is equal to A times R. Okay. So we say that P in R is prime if the ideal generated by P is a prime ideal. Okay. And we have already defined associates, so please keep that in mind. Okay. Right. So this definition is basically in accordance with the primes we deal with in integers, because we know that by definition of a prime ideal, this should imply A is in P or B is in P. Right. Therefore, in division notation, P is a prime if P divides AB, then P must divide A or P must divide B. Yeah. Now, this can be immediately observed that in any integral domain, prime elements are irreducible. Okay. And it's very easy to observe. Why? Let's say let P be a prime. Let P be a prime. Then this implies that the ideal generated by P is a prime ideal. Okay. Now see, P is a prime. That means that the ideal generated by P is obviously is a prime ideal. That means it's a non-trivial ideal. Therefore, P cannot be a unit. And obviously, we are not talking about the zero ideal in any sense. So let's keep it. Okay. Now let PB is equals to AB. Okay. Then this implies that AB, which is equals to P, is in the ideal generated by P. Right. So this implies that either A is in P or B is in P. So without loss of generality, let A be in P. Okay. We can do this. Then that implies I can write A as some P times R, where R is in R. So that implies that P is equals to AB, which is P times R times B, which implies P times 1 minus RB is equals to 0. Since P is non-zero, obviously we are not talking about P to be a zero element. So this implies 1 minus RB is equals to 0, or which implies B is a unit. Right? Therefore, P is irreducible. One of the factors is a unit. Clear? But the question obviously arises that is the converse true? Okay, is the converse true? Now, see the following. See the following example. Suppose we are in the ring Z root 5, Z root minus 5, sorry, which is the collection of all elements of the form A plus minus 5B, such that A and B are integers. Okay. Then observe that the element 3 is irreducible in R. Okay. The checking is quite easy. What we can do is is the following. That see, if I write 3 as, let's say, A plus IB, sorry, not A plus IB, I'm extremely sorry. This is an exercise you can do. I'm just giving a hint. A plus root minus 5B into C plus root minus 5D. Then I can also write, so I can take conjugates on both sides, right? So I can take conjugates on both sides, right? So it will become A minus root minus 5B into C minus root minus 5D. So what do we get multiplying? So multiplying we should get 9 is equals to A square plus 5B square times C square plus 5D square. Therefore, what are the possibilities for these? Because all of these are integers, should be integers. So this can be 1, this can be 9, this can be 3, this can be 3, or this can be 9, this can be 1. Right? But since obviously observe that, so both of them cannot be 3, right? For them, they can never be 3 because A and B are integers, right? So they can never be 3. So this is the only possibility for them left. But then we can observe that then if A square plus 5B square is equals to 1, that should imply A is equals to 1 and B is equals to 0. Right? Therefore, A plus root minus 5B becomes plus or minus 1. Anything plus or minus 1. So it's equals to plus or minus 1. And that's a unit in Z. Right? Pretty easily observable. And without loss of generality, I did this. You can also take this to be 1 and you will get the same conclusion. Got my point? Right. Yeah. Taking negative factors won't cause any problem, but you can't take negative factors, right? Because we are all dealing with positive integers. There are squares everywhere. Fine. Okay. But observe that, so what we get is that it is irreducible, but if I take 2 plus root minus 5 into 2 minus root minus 5, then this is 4 plus 5, this is 9, which is 3 square. So this is, therefore, 3 divides 2 plus root minus 5 and 2 minus root minus 5. But it is very clear to observe that 3 doesn't divide either. right? Therefore, 3 is not a prime number or prime element. Therefore, in general, what we conclude is that in general, irreducibility need not imply prime, right? But it holds when it holds if you're in a principal ideal domain. Okay. What do we immediately conclude from here is that z root 5 is not a PID. Okay. We'll write it, but let us first prove this. So over a PID, uh, we have elements to be prime if and only if irreducible. Okay, proof. Now one of the implications is already shown that prime implies irreducible. Okay, we need to prove the other case. So I need to show that. So we require to show that irreducibles imply prime. Okay, let's see. In fact, we will prove another version that irreducibles actually imply, and the ideal generated by irreducible element is actually a maximal ideal. But all maximal ideals are prime ideals, so the ideal will be a prime ideal. So our goal will be to do this. So if P is irreducible, then we will prove that the ideal generated by P is maximal, hence prime, hence P is prime. This is what we will show. Okay. So uh, let P be irreducible, and let's say the ideal generated by P is contained in some ideal M is contained in the ring R. But since R is a PID, this ideal must be generated by some element M, right? So this implies that the element P is contained in the ideal M, which implies I can write P as R times M. But since P is irreducible, this means that either R is a unit or M is a unit. What happens if M is a unit? So if M is a unit, then the ideal generated by M must be the whole ring R, right? But what happens if R is a unit, right? So then we can follow it in this way, right? If what happens if R is a unit? Please check it. Clearly, if R is a unit, then I can write M as some S times P, right? What does this mean? This means M is in the ideal generated by P because I can take R here. That means that the ideal generated by M is contained in the ideal generated by P. So in this case, the ideal generated by M should be exactly equal to the ideal generated by P. So we get two cases, right? Either the ideal in between is equal to the whole ring, or the ideal in between must be equal to the ring, be equal to the ideal generated by the irreducible element P, right? So what do we conclude? That the ideal generated by P is maximum, hence prime. So the upshot from here is that ideal generated by a irreducible element is maximal and hence prime. Yeah, over PIDs. Keep in mind, and that is why if you go back to the previous part, then we had said that the ideal generated by X is a prime ideal. We were working over a PID if you recall. We were working over a PID because we had assumed Rx is a PID, and X is irreducible over the ring of polynomials, over any ring of polynomials, right? So from there, actually, we could prove that since X is irreducible, so the ideal generated by X is a maximal ideal and hence a prime ideal. But we only required maximality, right? And we had there used the fact that prime ideals, non-zero prime ideals are maximal. But since X was irreducible, we could have directly proved that it was a maximal ideal. Fine. So, and another upshot of this part is that, therefore, z root minus 5 is not a PID. Because we had shown that here 3 is irreducible but not prime. Right? Fine. Now we will prove a very important property of prime ideals, of principal ideal domains, which will give us an interesting consequence as well. Okay, we'll see. Okay, so let me state it first. Let R be a PID and let A1 be contained in A2, be contained in A3, so on and so forth, be contained in R, be an ascending chain of uh, principal ideals. Then this chain must stabilize finitely. Must stabilize finitely. That is, so what do I mean by this? That is, there exists some n such that Aj must be equals to An for all j greater than equal to n. Yep. Okay. Let's see. Proof. Yeah. So let I see. Actually, the proof is in this way. Okay. We can in fact prove a sort of a general consequence that if I1 contained in I2, contained in I3, contained in so on and so forth is a ascending chain of ideals, Okay, it's an ascending chain of ideals, and you need such such sorts of arguments whenever you talk about maximal ideals. Okay, we won't involve the notions of existence of a maximal ideals everywhere or in every ring in some sense, talking like that. Okay, I try to bring up such a lecture in some other lecture where we will be talking about radicals and local rings, so on and so forth. There we will be requiring such an argument, or this is sometimes called a maximality condition. But nevertheless, what we want to say is that given ascending chain of ideals, there is always an ambient ideal which contains all of these. Okay. Then union of all these ideals is also an ideal of R. And if each of these are proper ideals, then this is also a proper ideal. Okay. Because obviously, if each of these are proper ideals, I cannot say one is in I. Right. Clear? Right. Why is it an ideal? That's also pretty easy check. See, if A and B is in I, then that implies that A is in II and say B is in IJ. If A and B are in the same ideal, then A minus B will be in that ideal, so it will be in the union. That's a trivial check. But if they are in different ideals, then if I is less than J, then I must be contained in IJ. That means A and B both are in IJ, and therefore A minus B is in IJ, and hence in the union. And similarly, if J is less than I, so then IJ will be contained in II, and then the same conclusion happens. And I being closed under multiplication by R is also trivial, right? Because if I choose any element, it's in some ideal. That ideal is closed under multiplication by R, so the whole ideal is closed by multiplication by R. So in fact, what we conclude from here is the following: that if I take I to be the union of all these ideals generated by AI, I greater than equal to 1, then this is an ideal. And since R is a PID, therefore there exists some element A in R such that I is the ideal generated by A. Clear? Got it? Now observe the following. Now what does this mean? This means that A is contained in the union, right? Right. So this implies that A is contained in the union AI, I greater than equal to 1. This means that A is contained in some AN, right? For some N. But AN will be contained in AJ for all J greater than equal to N, right? So what does this imply? This implies that the ideal generated by A should be contained in this, it should be contained in AJ, but the ideal generated by A is actually the union of all these ideals. So all these ideals must be contained in the union as well, right? So it must be contained in. So what does this imply? That AN must be equals to AJ for all J greater than equal to A. Right? So it must stabilize finitely. Right? So the next part of this lecture, what we will do is we will prove this very interesting consequence after defining UFDs, that all PIDs are UFDs. So once we prove that, posteriori we can conclude that Euclidean domains should imply PIDs, which should in case imply UFDs, right? So if you start with the Euclidean domain, that will automatically be a PID, and that will then automatically be a UFD. But we are already proved that PIDs are not or not does not imply Euclidean domain, and we will in fact prove that UFDs also does not imply principal ideal domains. Yeah. Okay. So meet in the next part. And again, always prefer you guys to see the lecture as a whole, because I'm just pausing and starting for the new part. But nevertheless, this pause is for you to revise whatever we did till now. Okay. So Professor S. Kumaresan says a very important thing: pause, review, proceed. Right. So I'll prefer the same as well. Fine. Let's continue with the new part. Right. Now let us introduce the notion of unique factorization domains. Okay. So unique factorization domains. Okay. So what is the basic definition? Analogous to the notion of integers, that every element can be written as a finite product of prime numbers, prime elements, and this representation is unique up to some factor. Okay. So definition: an integral domain R is said to be irreducible. Sorry, I'm mixed it. Sorry. An integral domain R is said to be a unique factorization domain if for all non-zero elements R in capital R, which are non-units, number one, R can be written as a finite finite product of irreducibles, finite product of irreducibles, and number two, the factorization is unique up to associates. Okay, what do I mean by this? So let me just briefly do explain it a bit. So firstly, what I claim is that you can write R as some P1 times P2 times P3 till some Pns, where each Pi is is an is an irreducible. And if you write it as if you can write it as Q2, Q3 till Qm, then firstly n must be equals to m, and each Pi must be an associate of Qj's for all I. Clear? That is, these Pi's or respectively these Qi's are some unit multiples of the other. Clear? Now immediately you can see something that clearly F is a UFD vacuously, because every non-zero element is a unit. Is a UFD vacuously, and we will get hold of some very important examples a bit later. Once we claim that PIDs are actually UFDs. Okay. Now also you can see that this ring is not a UFD. Why is it so? Because let's see. Let's see. Let us use element 6. I can write it as 2 times 3, and I can also write it as 1 plus root minus 5 into 1 minus root minus 5. Right? Yeah, both are irreducible. 2 and 3 are irreducible. These two are also irreducible. But none of them are pairwise associates. Okay. To prove this, I'll leave it as an exercise to prove this. And to get hold of associates, you need to get hold of the units in Z root minus 5. Okay. To do this, what you need to do, you need to take this product a plus root minus 5b times a minus root minus 5b. I'm doing a mistake every time. So c plus root minus 5d equals to 1. Then take the conjugates and then multiply. Then you will get a square plus 5b square times c square plus 5d square is equals to 1. Conclude from here what should be the units. And then you will get hold of the fact why they are not associates. Why none of them are pairwise associates. Okay. I think you can do this a bit. In some other lecture, okay, after we complete the fundamental part of these things, because our main goal is to talk about polynomial rings, which we will be completing in the next lecture probably. After that, we will give a dedicated lecture on ring of Gaussian integers, and there are a lot to talk about in this case. Right? Now, observe something. Observation. Observation. Suppose R is a UFD and P in R is irreducible, such that let's say P divides A. Okay, A and B are elements in R. Clear? So that implies I can write AB as P times C. Clear? Now we are in a UFD, right? Since we are in a UFD, I can have a factorization of A as, let's say, A1, A2 till AN, and I can also have a factorization of B, let's say B1, B2 till Bn. This should be equals to PC, right? Getting my point? But what can we conclude further from here? Okay, so the following comes into observation. Okay, what I want to say is basically that see, these two are, if both of these equal to some element, then these actually give me two distinct factorization, okay, of, let's say, A B equal to R in some sense. Okay, therefore these two factorizations must be unique up to associates. Up to associates. What does that mean? That means that either P must be associated to some AI or P must be associated to some Bj or some I and some J. Right? So without loss of generality, let P be associated to A1. Okay. Why can we say that? Okay, at least I can, without loss of generality, I can say that P is associated to some AI, but then I can just reiterate. By reiterating A1, A2 till AN, we can say that is just, just permute these factors. We can say that P is an associate of A1. So that implies I can write A1 as some U times P, and in that case, my A, this becomes, which was A1 times A2 till AN, this becomes P times U A2 till AN. So this implies P divides. Right? And since everything was without loss of a generality, so therefore what do we conclude? That P divides AB should imply P divides A or P divides B. So what do we conclude from here? This concludes that P is a prime element. right? So previously we have shown that over a PID, every irreducible is a prime. Here we show the same thing that over UFDs as well, every irreducible element is a prime. Thus, now primes are irreducible in every integral domain, every ring. So, got my point? Okay. Fine. Now, due to this notion of associates, we can do one thing. Observe that if you have, let's say, factorization, say a1, a2 till an equals to, let's say, b1, b2 till bn, because either a must be obviously equal to n, then what we conclude is that ai must be associated to some bj, or ai must be some unit multiple of bj, and it will happen for every such factor, right? So in fact, in that case, the uniqueness, in terms of uniqueness, okay, what we can do is then we can factorize in terms of a unit multiple. Okay, this factorization, say a is equals to a1 till an, this can be unit determined by a unit multiple of it. So in some sense, we can also use a factorization of this form. Okay, because at least one will always be a unit, right? Getting my point? Okay. Now we had proved previously that in every Euclidean domain the GCD exists. Then we had also proved that over a PID GCD always exists, because the GCD by definition is basically just the generator of the ideal generator of any pair of elements. Now, so I can in fact explicitly give a structure to the GCDs in UFD. Okay, so this is a proposition, but I'm not going to prove it. I'm going to leave it as an exercise proposition. And let A and B be two non-zero elements of the UFD R, such that, let's say, I can write A as some U times P1 epsilon 1 till say Pn epsilon, and I can write B times some unit multiple V of P1 F1 till Pn Fn. Then D is equals to P1 times the minimum of epsilon 1 F1 till Pn times epsilon n Fn is the GCD of AB. Clear? Right. If the exponents are 0, then the GCD will be 1. Right. And you can just prove it by keeping in mind the exercise. So you can just prove it by keeping in mind what you do in usual division in case of rings of integers. Okay. And now we come to our main result. Okay. And this is the final result of this lecture. Theorem. Every PID is a UFD, and posteriorly, what we conclude is that Euclidean domains imply principal ideal domains implies unique factorization domains. Clear? Clear? Okay. Fine. So yeah, so let's do it. Right? Let's do the proof. And I say that the proof is not difficult. It's just you just need to understand things. And whenever we are proving things about UFD, always need to keep in mind that we are sort of working in rings. Okay. See, proof. See, the only problem for a ring being a unique factorization, or rather one of the problems for a ring to be a unique factorization domain is if the factorization does not terminate finitely. Getting my point? Right. Let me write it in this way, that the problem, or rather one of the problems for a unique factorization, for a ring to be a unique factorization domain, is if the factorization of some element does not terminate finitely. Okay. So our first step should be resolve this problem. Okay. Now let's see. Let R be an element of capital R. Capital R is a PID. Okay. Where R is non-zero, R is non-unit. R is non-unit. If it's a zero or a unit, then there's nothing to prove, nothing to deal with, right? Because after all, we need to write it as a product of irreducibles in order to prove unit factorization. Okay. Now, if R is irreducible, right, then R equals to R is a factorization, right? So we are done. So suppose R is reducible, okay, and let yeah. So by reducibility, I can write R as R1 times R2, right? Where neither R1 nor R2 are units, where neither R1 nor R2 are units. Now, if both R1, R2 are irreducible, we are done, right? We're done with the factorization. Nevertheless, we have not proved it unit, we do not require it at this point. So R1 and R2 are irreducible, we are done. Okay. So let, without loss of generality, okay, let me write it as R11. Okay, let me do it in this way. Um, yeah, fine. No, in the first step, let it be R1 itself. Okay. Hmm. Sorry. Right. Wait a minute. Right. So, okay, let me, because I want a good iteration, both R1 and R2. So let without loss of generality, R1 be reducible. Okay. Into R1 is equals to R11, R12. Right. Again, if R11 and R12 are both irreducible, we are done. As then I can write R as R11 into R12 into R2. So this is a factorization. Okay. Else, again without loss of generality, let R11 be reducible. So I can further factorize it into R, let's say R21 into R22 and so on and so forth. And or rather, let's say R111 into R112, so on and so forth, right? I can keep factorizing it into a product of pairs. And whenever I'll reach a point where both are irreducible, we are done, right? And if one of them is reducible, then we will continue this process. So what does this actually give me? So clearly observe that the number we started with, if I generate an ideal with it, then it should be contained in the ideal generated by R1 because R1 actively divides R. But then this must be in the ideal generated by R11, and this process will continue, right? Till we reach a point where both the factors will be irreducible. But the point is that what is the guarantee that we will reach that point when both the factors will be irreducible? And equivalently, we can say that what is the guarantee that this chain of ideals will stabilize? Now observe carefully. If this chain stabilizes finitely, right, then the above process terminates finitely, right? Terminates finitely. And now recall that we had proved a very important property of PIDs that such a chain will terminate or will stabilize finitely. Got my point? Right? So therefore we conclude, therefore, since such chains stabilize finitely over PIDs, our process will stop finitely, giving a factorization of R into product of irreducibles. Clear? So such a actually this proposition which I had proved previously, that such ideals must stabilize. This is something called an ascending chain condition. Ascending chain condition, or what we call ACC. Okay, rings in which ascending chain conditions hold in general are what we call Noetherian rings. Yeah, I guess we call them Noetherian rings. I don't exactly remember, but yeah, I think we call them Noetherian rings. Please verify once. Yeah, there is also something called an I guess an Artinian ring where descending chain conditions hold. Right. Yeah, two types of rings are very important in study. One are Noetherian rings and one are Artinian rings. Okay, so so basically PIDs, rings which are PIDs, are basically Noetherian rings. Right. Okay. Yeah, these are basically topics of advanced ring theory, typically what we call advanced ring theory. But nevertheless, let us not get into that. So what we conclude is that if we start with the PID, then we can write an element into a product of irreducibles finitely. Now the only question which is left to be attained is that whether this factorization is unique up to associates or not. Right? That's the only thing which we need to talk. So now let's see. Right? So to prove uniqueness, we induct on N where we assume R is written as P1, P2 till Pn, and let it also have a factorization Q1, Q2 till Qn. Okay, where each Pi and Qj are irreducibles. Now observe the following. Now the argument is pretty easy. See, now P1, P2 till Pn equals to Q1, Q2 till Qm. This implies that P1 divides the product Q1, Q2 till Qm. Since P1 is a non-zero irreducible element, or rather it's non-zero by definition of irreducibility, so since P1 is irreducible, P1 is prime, we have proved previously. So P1 must divide either of them. That means P1 divides one of them. So some Qj for some J. Right? So again, by reiteration, let P1 divides Q1. Got it? But P1 is irreducible, hence it's a non-unit. Q1 is reducible, so it's a non-unit. But since Q1 is irreducible, to write Q1 as a product of two elements, one of them needs to be a unit. So that implies that there exists some unit U such that I can write Q1 as U times P1. Right? Once we do this, what do we get? So therefore, I have P1 times P2 till Pn equals to U times P1 Q2 till Qm. But then we are working in an integral domain, so cancellation is there. So I can cancel out P1s. So what I'll get is that P2 till Pn is equals to U times Q2 till Qn. Right? Right? So I can just take this to be say Q2 prime till Qn. Right? Right? But then observe that Q2 prime is an associate of Q2. Right? And Q2 is irreducible. So Q2 prime is irreducible as well. Right? This is also an exercise we can easily prove that if P is irreducible, then some unit times P is also irreducible. Very easy check. Okay. So Q2 prime is also irreducible. Therefore, if I do induction on n by induction on n, okay, we can conclude that each of the factors on the left matches bijectively because if we resolved Q1, we resolved P1 and correspondingly we resolved Q1, right? Because the factorization is still equivalent to the factorization Q2 till Qm because Q2 prime is again irreducible. So once we resolve one element from the left, equivalently we are resolving one element from the right, right? So each factor on the left matches bijectively up to associates to the ones on the right. Clear? Clear? In fact, to the ones on the far right. Okay. I can talk about the elements from the last and hence to the elements in the middle. Clear? Why can I say so? That bijectively up to associates far right, I can go via reiteration. Okay, I can iterate. What I'm trying to say that I can iterate these PIs in such a way that say P2 is associate to QM, P3 is associate to QM minus 1, so on and so forth. That is what I'm trying to say. Okay, so it must be. So if I come below from the right hand side and here I ascend in the left hand side, so after all every element must resolve bijectively, right? And hence M must be equal to N and the factorization is unique up to associates or a multiple or a unit multiple. Factorization is unique up to associates or a unit multiple, equivalently a unit multiple. Clear? So this immediately proves a very important part of number theory, which is that I'm writing it here, that Z, what we call the fundamental theorem of arithmetic. That is the factorization, in fact the prime factorization of Z is unique, right? Because Z is an Euclidian domain, so it's a principal ideal domain and hence a unit factorization domain. Getting my point? Yeah. So it's already a very long lecture, so I'm leaving this lecture here. In the next lecture, we will start with irreducible polynomials, and then in some other lecture, we will talk about the Gaussian integers and some other insights. So meet you guys in the next lecture.